Okay, so great. So what we're going to look at now is loss functions as we project them onto a two-dimensional plane. And then how can we compute the gradient? How can we read or visualize the gradient? Okay, so here I know this is not a loss function because it's like obviously it's not convex. It has a maximum. But if you flip it, right, you're gonna have a minimum, right? So imagine if we're flipping it and just your head. But here, what do we have? So we have two directions. So for example, if we fix the W1, so it's a two-dimensional loss function, and this is, you know, the first dimension is W0, and we have W1, so I should change those, right? So here we have dimension 1, dimension 2, or feature 1 and feature 2. And if we fix the first, like, one feature, like, we can see how the loss function changes across the second. If we fix this one, we can trace its changes, right, along the second dimension. So this, now I'm changing everything. This should be W1, right? And then if we fix also the W1 right here and follow the line, right, we project it, we can see the shape of the loss function in two-dimensional space, right? And this is the first dimension. Okay, so this is another way of reading high-dimensional functions. So if you guys remember previously, what we saw the what we call the level curves, or the rings. We also call them the contours of the function. So we just, you know, look at those contours and then we project them onto a two-dimensional plane, and you can actually read your function. You can see how, you can't really see how it looks like, but you can at least monitor its change, its, you know, the way it changes. Because here, if it's like, you know, equidistant, you can think of it as probably maybe a uniform Gaussian, right? So looking at those plots, it gives you some information about the shape of your function. Now let's look at this case. So here, what do we have? We have this loss function, and it's a convex function, right? That depends on two variables. So our W has two dimensions, W0 and W1, and then we're plotting it right here. So this is, you know, the first variable, W0, W1. These are the contours of the function. And as you can see, if we go, the values that the function is taking in the middle are very low because we have light blue. But then as we go further, the blue becomes darker. So the dark regions right here, they present areas where the function is taking high values. Okay, so in this direction, the loss function L of W decreases, and the opposite direction it increases. Okay, so if we look, for example, let's say we have an initial point W 0. So this is, you know, superscript, it means our initial point. Subscript, it's the dimension. So you have dimension 0 and dimension 0 and dimension 1. And we have our initial point right there, and we want to find the optimum W star. So the W star would be exactly this point at the center of our circular contours. Okay, so the gradient, one rule to take is important property of the negative gradient direction. So it is always perpendicular to the contours, or what we call the level curves of a function. So this is universally true, which means whatever the function you have, whether it's, you know, concave, convex, your gradient is always perpendicular to the level contours. So it's like here it acts like this is exactly the normal direction to so this is the tangent to the contour at this point W0, and the gradient is exactly the it's the normal vector. Okay, it's perpendicular to this contour. Now, if we're gonna look at this, so in this plot, it's quite nice because you can see how the gradient behaves. You can visualize it. You can plot it. It's not like, you know, in a high dimensional space, it's not very feasible. So this is different from the tangent to a one, you know, like one-dimensional function. So in a high dimensional, for high dimensional multivariate functions, it's easier to plot them using the contours, right? Project them all, like all those shapes. You project them onto your plane, okay? And then you can see how your gradient, you can visualize and plot your gradient. Now, this is, for example, the value that your function is taking in the orange ring. Now, if you look at the pink ring, it should, the C here, the constant C2, it should be lower, right? So at this ring, as you can see, like we saw this before in the Gaussian function, so the ring should have lower values because we're going down, right? So while it's like if you flip it, it should decrease because it's a convex function. Now, let's look at this case. So this is, for example, another plot of a loss function. So we can here see that we have a minimum right there, and we have a maximum. But the problem is generally you will find the stationary point. You can see them easily in these curved plots, but you might not, if you're tracing the values, if you know the values of your function in each contour right here, you would know it's a maximum or it's a minimum, right? So if it's like the values are decreasing, so it's a minimum. If they are increasing, so if it's a maximum. Okay, so that's one way. Just by following the values that your loss function takes at each of those contours, because these are, you know, your loss function is constant along each of those contours, okay? So now let's look at these two cases. So generally for, we have two different functions, loss functions right here. So this is the first one and this is the second one. And you can see that this is a wavy one, right? This seems to have different, maybe like it's a non-convex function. It has multiple local minima. One of them probably is global. So we're starting off at 3 different points. And the gradient always, it points to, it's perpendicular to the contour. So this is your contour right here. This is your point. And the gradient points towards the optimum. It should be perpendicular to your contour. Same thing right there. So we're starting off at this point, W0. And this is where we're heading, right? And then you will update this step by step. So in this case also it's the same, so you can see where your points are pointing. So whatever, like this is just to show you guys that you know, this rule applies to any function, okay? So now let's look at like at this property, why we're having this, why the gradient is perpendicular to the tangent, right? To this function, for example. So if you remember, this is just a simple, this is actually the definition of a gradient. So what we have, let's say our function is differentiable at some input point A, okay? And then in this case, we're going to take the A will lie on the contour where L of W equals L of A equals is a constant. So which means, you know, we're taking a point and then we're like picking all the points, taking the contour where all the points have exactly the same, you know, a loss value. So we're cutting our curve at that L of A, okay, at that value. We're cutting it and projecting it. So then when we take another point, be very close to A, so this is a local approximation, and very close to A, then we have by definition the gradient will be like times the vector like A minus B, so this is the small vector will be equal to 0. So in this case, it means that their dot product is equal to 0, right? Y, which means this x is perpendicular to y, okay? And this is exactly what we have here. So if we write the linear approximation of our function, and because these guys lie on the same contour, okay, so they have the same values, so this will be equal to 0, okay? So it's kind of, you know, kind of simple. Now, let's look at the two issues with the gradient descent. So the first one is the zigzagging. behavior of the gradient descent, and this is related to the direction of the negative of the gradient, right? So this is a big problem because it slows down the convergence as the gradient oscillates. So it keeps flipping, like, you know, its direction changes a lot, and it takes a lot of time to converge to your optimum. So this zigzagging behavior slows down the convergence. So we're going to look at this function right here. So a is equal to 0, b is equal to, also it's a null vector. And let's see how for different c values, how the gradient direction changes. So first, so this is our quadratic loss function. This is our initial point W0, and we run the gradient descent for just 25 times. And these are actually the C, our C matrix that we use to plot this function. So you can see that as we change the value right here, the function gets elongated. The rings, right? They get stretched or elongated along the W0 dimension, right? So this is W0, W. So here, in the first case, you can see some zigzagging of the gradient, so I'll explain it. But in the second case, it's like, we're elongating more, we're stretching more the function along the W0 dimension. And here you can see the rings, they become more spaced out. In this case, we stretch it even more, so they become almost parallel, right? All those contours. So it's too stretched out, right, along the W0 direction. Now, why we're having the zigzagging property, it's mainly because the gradient is perpendicular to the contour. So if we start off right here, let me choose another color. So if we start off right here, okay, that's our W0, it's 10, 1. And 1. Okay, so then how do we find the gradient? We need to plot the perpendicular to that contour. Then we hit our next point right here. Then at this point, we're computing the gradient again. And then again, it's the same thing. We're hitting another point at this contour, computing the gradient, the perpendicular. And actually, these are infinite contours. But here, because we are sampling, we probably selected, a few of them, right? But this is a continuous space. It's a continuous function. So all of those are actually, there are some contours here. So these points do not lie in empty space. They lie on contours that we did not plot, okay? So, right, so if you can see, guys, what is happening right here is, like, first we had this direction of the gradient, let's say the green one, and then we're changing the direction. So the direction becomes like this. So if I take this guy right here and I plot it there, just a parallel, you can see a big flip or an oscillation in the direction of the negative of the gradient. So it's going upward and downward, like this way. So this is the zigzagging property that we see right here. And this is, like for the second case, we have more zigzagging, and here it's even massive zigzagging because in this case you can see the contours are parallel, so it's like the loss function is more stretched out along this direction. It takes more time to converge. So the problem, as I mentioned, that zigzagging is caused by the negative gradient direction being constantly pointing perpendicular to the contours of the loss function. And if we plot right here the loss function, so remember, guys, we want to minimize this, right? And we have we plot the loss function for different WKs from our starting point. So this is our starting point right here. And we're having different losses, so the loss 1 and 2 and 3. And you can see that for the first one, we have a very nice decrease. But then at this level, all of this, because of the zigzagging, the loss is being very, like it's slowly decreasing. So this is what we call the crawling process. So it's like, like the gradient or the loss is like very slowly decreasing. It's taking a lot of time to go there. So ideally, you would have something, I don't know, like this. Okay, so maybe just it decreases so fast, it doesn't take a lot of time to reach the optimum, right? So the problem is even more, how do I say, it's like more, it's clearer with these, with the second run and also the third one, and you can see the decrease is very slow. It takes a lot of time. You don't have a nice, quick decrease of your loss function, okay? So this is a nice visualization, a plot of the gradient of descent direction for the first 9 steps. And you can see that in the first step, we have exactly, for example, this direction. Remember, it's perpendicular to the contour. And then in the next step, we have completely the flipped direction, okay? So this oscillation process is what makes the gradient, the negative of the gradient direction zigzag, and then you're having a slow convergence for this case. Now for the third case, which is the worst one, you can see that it's actually, you have completely the opposite direction. So it's like a 180-degree flip. This is why it's taking even longer. Now, how do we solve this problem generally? So one way is to decrease the step length value alpha. So if we decrease the alpha, you can see in the third case, we have more, like we're avoiding the zigzagging behavior of the negative of the gradient, but still we have a very slow convergence, okay? So we did not solve the problem, okay? So that's issue 1 that you guys need to remember. Yes? What if? A varying alpha, that's a very, yeah, that's, so adaptive alpha, that's another solution. So basically you can start with maybe slightly big alphas and then, diminish them at the end or increase them. So yeah, so depending on how your loss function looks like. So adapting the alpha according to where you are at on your plot, on your function, that's a good strategy, yeah. So adaptive gradient descent, yeah. Cool. So the second issue is what we call the vanishing gradient or the vanishing magnitude of the gradient. So this is basically, remember guys, when we looked at the gradient descent, so this is our update rule, right? So the difference, the magnitude, the step, how the length of this step. So if we have here, this is our WK minus 1, WK, and this is the distance we have crossed. It's exactly alpha times the magnitude of the gradient, right? So if you can see, like in the first strides, this one, like if we go from here to there, so let's say we're moving to this point, then computing the gradient with an alpha, moving right here. It's because the gradient has a large magnitude, so the slope is quite high, right? You have a big slope right there, so the magnitude is quite high. So you're jumping far away, even if your alpha is constant, right? But the problem appears when we reach an optimum, when we reach, for example, a stationary point, a minimum or a saddle point, and you can see that because your gradient has it has a very almost a zero magnitude because it's flat, right? It's getting flatter. So the gradient here will be almost equal to 0. Your alpha is constant, so your steps will be very, very small. That's why we have the crawling behavior, or what we call the vanishing gradient. The gradient is vanishing slowly. Its magnitude is becoming smaller and smaller and smaller, close to 0, and that's exactly what we want. But this is problematic because you guys can see we have a nice jump from here to there, but once we reach a flat area where the gradient magnitude is close to 0, we have this crawling process, which means we have many iterations to finally find the optimum, okay? But right here, it got stuck right there, okay? So this is quite simple, and this is what we call the slow crawling behavior of gradient descent, and it occurs at stationary points, so you can see this at saddle points right there. So the algorithm stopped right there. So it did not even continue to find the global minimum in this case. So this is problematic. And also, for example, this is the last example. So we have our initialization for our loss function right here. So this is our W0. And you can see that even after 1,000 steps, this point has not moved. It was stuck. Why? Because we have a long, narrow valley. So you can see it right there. So our point is here, okay, somewhere here. And it did not move at all because it's so flat. The gradient is it has already vanished, right? Okay, great. So that's it for today. Do you guys have any questions?